Section 7.3, Day 2, Sampling Means. After this lesson, you should be able to explain how the shape of the sampling distribution mean is related to the shape of the population distribution, and also apply the central limit theorem to help find probabilities involving a sample mean. Most population distributions are not normal. What is the shape of the sampling distribution of sample means when the population distribution isn't normal? It is a remarkable fact that as the sample size increases, the distribution of the sample mean changes its shape. It looks less and less like the population and more like a normal distribution. When the sample is large enough, the distribution of sample means is very close to normal, no matter what the shape of the population distribution is, as long as the population has a finite standard deviation. As a definition, this definition is known as the central limit theorem. If we draw a simple random sample of size n from any population with a mean of mu and a finite standard deviation of sigma, the central limit theorem says that when n is large, the sampling distribution of the sample mean x bar is approximately normal. How large a sample size n is needed for a sampling distribution to be close to normal depends on the shape of the population distribution. More observations are required if the population distribution is far from normal. So if I have a very skewed distribution, the number in the sample needs to be larger. If the population distribution is close to normal to begin with, your sample size n could be smaller. Take a look at this distribution here. I want to describe here the shape of the sampling distribution as n increases. What do you notice? Okay, in this first picture, again, this is a simulation distribution from an applet on Rice University's mathematics website. If I take a sample size of 2, so I'm taking two values from the population distribution, averaging those together and plotting that, and doing it many, many times. Notice here I have several peaks. It's definitely not normal. If I increase the sample size to 5, the distribution looks like this. It's starting to become more normal. It is still a little bit skewed to the right. Here's a sample size of 10, still a shade skewed to the right. But when I take a sample size of 25, it begins to look more and more like a normal distribution. So the normal condition for sample means. Remember, for proportions in the previous chapter, the normal condition was satisfied if n times p and n times 1 minus p is greater than or equal to 10. This will be our condition for sample means instead of sample proportions. If the population distribution is normal to begin with, then so is the sampling distribution of x bar. This is true no matter what the sample size n is going to be. If the population distribution is not normal, the central limit theorem tells us that the sampling distribution of x bar will be approximately normal in most cases if n is greater than or equal to 30. So to be able to perform normal calculations, I should have a sample size that's greater than or equal to 30. Then it does not matter what the original distribution looks like. Based on service records from the past year, the time and hours that a technician is required to complete preventative maintenance on an air conditioner follows a distribution that is strongly skewed to the right, where most likely outcomes are close to 0. The mean time is mu is equal to 1 and a standard deviation sigma is equal to 1. These are parameters because all of the data has been collected and this is from the population. So here's what I want to do. Your company will service a simple random sample of 70 air conditioners. You have budgeted 1.1 hours per unit, and I want to know if that'll be enough time. Since the 10% condition is met, more than likely there's more than 700 air conditioners in this population. The sampling distribution of the sample mean time spent worked on 70 units has a mean that would be mu sub x bar, which is equal to the population mean of mu, which would be 1, and sigma sub x bar would equal sigma divided by the square root of n, or 0.12. The sampling distribution of mean time spent working is going to be approximately normal, again since my number in my sample is greater than or equal to 30, and it's going to have a mean of 1 and a standard deviation of 0.12. Here is a graph of what I'm looking for, and again this is a good idea to always put a picture down when you're trying to solve this if you're doing a free response type question on a quiz test or the AP test at the end of the year. If I standardize this, find my z-score is going to end up being 1.1 minus 1 divided by the standard deviation of the sampling distribution, which is 0.12, which gives me 0.83. So I'm trying to find the probability that z is greater than 0.83. Using the z-table, I end up with 0.2033. So if I budgeted 1.1 hour per unit, there is about a 20% chance that the technicians will not complete their work within the budgeted time. Quick lesson summary over section 7.3. When we want information about a population mean, mu, for some variable, we often take a simple random sample and use the sample mean x bar to estimate the unknown parameter mu. The sample distribution of x bar describes how the statistic varies in all possible samples of the same sample size from that population. The mean of the sampling distribution is mu, so that means that x bar is an unbiased estimator of mu. The standard deviation of a sampling distribution of x bar will equal the standard deviation of the population divided by the square root of n for a simple random sample of size n, if the population has a standard deviation of sigma. This formula can be used if the population is greater than or equal to 10 times the number in the sample. When we choose a simple random sample of size n from a population with a mean of mu and a standard deviation of sigma, if the population is normal, then so will the sampling distribution of the sample mean x bar. If the population distribution is not normal, the central limit theorem states that when n is large enough, the sample distribution of x bar is approximately normal. We can use the normal distribution to calculate approximate probabilities for events involving x bar whenever the normal conditions are met, and here they are. If the population distribution is normal to begin with, so will the sampling distribution. So I can go ahead and use my normal calculations. If it's a skewed distribution, if n is greater than or equal to 30, the central limit theorem tells us that the sampling distribution of x bar will be approximately normal in most cases. This is the end of section 7.3. In chapter 8, we will begin to calculate confidence intervals and doing significance test.